Today we will talk about Ppk, Cpk, process capability, and Six Sigma, and their importance for manufacturing devices, especially biomedical devices. For that, we're going to use an example. We have a catheter here, and we have received a batch of tubing that we will use for manufacturing of this catheter. We will look at specifically at outer diameter of the tubes. That is a critical dimension for us for the manufacturing of this catheter. We will look at the variation of outer diameter and how much this variation will impact our catheter manufacturing. The first step is to basically measure the parts. We cannot measure the whole lot, but we can take a sample. We take 20 samples random from the bag and we measure the outer diameter. Outer diameter is a CTQ, is a critical dimension for us, and we use a 3-axis Zumbach laser to measure the OD. Basically, we'll measure OD in 3 axes and take an average of 3. We have measured all 20 samples here, and for the outer diameter, the specification is 1 millimeter plus minus 0.1. So basically, the upper limit is 1.1, and the lower limit is 0.9 millimeter. If you go lower than 0.9, the part is too small, and we'll have problem with that. If we go above 1.1, the part is too large, and again, we will have a problem with that. So the limit is 0.9 and 1.1. Now that we have measured the data, we bring it into the mini tab and we use process capability chart for analyzing the data, knowing that the data are normal. On top left, we have the lower speak limit that is 0.9, the upper speak limit that is 1.1. We have sample mean, we have the sample number of the sample that is 20. And we have two important parameters, a standard deviation overall and a standard deviation within. The difference between these two would define the differences between the CPK and Ppk. You know that the CPK is pretty high here, but the Ppk is very low. So we're going to explain that in next slide. So when you import the data into mini tab would divide the data into subgroups. Like for this case, it would divide it in 5 subgroups. Each 5 subgroups is 4 measurements. Within each subgroup, the standard deviation is small, is 0.015, comparing to overall standard deviation. That's for 20 sample, the standard deviation is high, is 0.049. That's higher than the standard deviation. And the reason is for that is that the process is drifting. That's why if you look at like one subgroup, that is one segment of the process or one frame of the process, the standard deviation is not that big. But as the process go on, you will see that, oh, you have more there's more variation, and that's why the standard deviation overall is higher, and the Ppk that is calculated based on that would go down. So if you look at the CPK, then the time of measurement is important because now you have subgroup, each subgroup after each subgroup. So how you collect the data is important for CPK, but for Ppk, it doesn't matter because it would sum all the 20 samples together. So for this particular case that we are randomly taking 20 samples out of the bag, CPK is not, it doesn't tell us anything. It basically is what we have to look at it is Ppk, the overall standard deviation. CPK is only important when you are looking at the process, when you want to look how process is moving, how each subgroup is doing. That's the difference between CPK and Ppk. And that's the reason here that the Ppk is 0.65, while CPK is very high. So CPK is calculated as the upper speak limit minus mean divided by 3 standard deviation. Ppk basically on the top is the same as upper speak limit minus mean divided by 3 standard. The only difference here is the standard deviation that you define. For PPK, the standard deviation is the overall. For CPK is a standard deviation in subgroups. That basically you take an average of a standard deviation of the subgroups. And because your standard deviation within subgroups is a smaller, like the average of those, small one is a small, is then your CPK comes, higher than PPK. One of the consequences of having a low PPK like 0.67 is that your out of spec part is it goes up. So when we look at the bottom left, is part per million out of spec is 43,677 parts per million that is out of spec. That is pretty significant. A ppk of 0.67, the picture that we get from that is that the process is not good. It means that the variation is high and the sigma level is about 2. Basically, you multiply your ppk by 3 and that would give you the sigma level. If you go higher in sigma, let's say you increase your ppk, a ppk of 1.3 accounts for a sigma of 4 level. That is pretty standard in industry. You can go higher and target 6 sigma. Basically a 6 sigma, that means that your ppk is 2 and you are near perfection. That means from 1 million samples only 3.5 defects are present. For this case that we are now measuring, we can tell that about 4.5% of spec are total are out of spec. That is about 45,000 parts per million. So what is Six Sigma? Six Sigma basically is a process improvement method. So you use some steps to improve your process and reduce your variation. That's the key. When you are reducing your variation or you're increasing your ppk, you bring in more consistency into your part. Now you'll have more certainty about your product. So the first step is to define. Clearly state the problem and customer requirements. So you see that my OD is a critical dimensions. And then how you want to control that, basically. Then measuring is very important. You correctly measuring the OD, you analyzing the data, they're finding the root cause, what is contributing to variation, what is causing the OD to like if you're doing extrusion, what is the problem with fluctuating the OD, what is causing that. Improve, that is basically defining design of experiments or the other study that reduce this variation, and basically you identify the variables in process that would impact this OD variation. For example, your pressure at the die, your temperature, or your water bath distance, and do a study, a DOE, and then you look at your signal, that is OD measurement, and then start analyzing the data and see how you can optimize it to reduce the variation. Once you determine that and find out, okay, this is the variables and I have to control it within that range, or in that process, then you look at, okay, now control it. How you make sure that each time you are within that process window, and putting in place the work instruction, the charts, the training, that okay, when you run this process, you have to make sure that you stay within those processing window. If you go out of that, then the variation would go up, and then we get a lower ppk.